It's a big pleasure to speak at this occasion. It's a great honor to speak at this first Ars Mathematica in Bielefeld here. I think I need to improve on my reading comprehension because I think when I was initially invited, I didn't even realize that it would have also this this poetry aspect to it, and it was really interesting to listen to the talk before. I found it very interesting. Right. The other thing I just wanted to say up front is that I'm probably speaking too fast and not clearly enough. So if I do so, please stop me and I will try to slow down, which is also good because I think I have too few slides and so my talk might be over way too early. Maybe I should say that in my work, I basically don't use any technology, and I kind of hate technology, and I hate to give Beamer presentations. So to the universities, please always install Blackboards in lecture halls. I feel like I don't know, I don't have my instrument at hand, so I need to do my best, but okay, let's see how it goes. All right, another thing I wanted to say before I really start my talk is that I think it does actually connect quite a bit to the previous talk we saw. On the one hand, there was this theme of p-adic numbers that were maybe not quite explicit, but certainly implicit in the talk. And there were quite a few pictures which are very similar to pictures that maybe will come up in a very similar form in my talk. The other thing that inspired me, and maybe, I don't know, I think it's a usual thing with poetry that you maybe interpret this in things that connect to you and maybe not in the originally intended ways. But this idea of a world in a world and also this world gestalten very much reminded me of a course I'm giving, lecture course I'm giving right now at the University of Bonn, where, I mean, one of the starting points is to resolve this usual conflict that in mathematics that already maybe Cantor realized that you cannot have a set of all sets, or you can, I mean, usually if you want to collect all things of a certain type together, then it's a bigger thing, so it can't really be a part of itself. But it turns out that using this language of categories, so where maybe all sets together, they shouldn't form just a set, they should form a category. There should be maps between sets that you also remember. And so in my course, it's important to talk about categories of categories and categories of categories of categories. And there is actually a way to have a category of categories that contains itself without a contradiction arising, which is a bit surprising, I think, because I think usually mathematicians have come to believe that such a thing could not consistently exist. And then all these complicated categories of categories of categories together, there is a certain way to think about this as a geometric object, and we needed a term for this type of geometric object, and eventually we settled for the term Gestalt. So, right, with that out of the way, let me start my talk proper. This didn't work. Swipe the other direction. Now it starts. Right, so here's a little bit of a outline of what will happen in this talk. So first I will start with a brief introduction, like trying to set the scene of what's about to come in some detail. Then there will be actually a somewhat long section recalling very basic school level material about the real numbers, but for a reason, because I think there's something I only understood about the real numbers a couple of years ago, and I want to kind of try to get that point across, that there is something very, very basic about the real numbers that one kind of often doesn't see. This will then bring me to the core part of this talk, which is this notion of condensed sets and how it relates to a more classical notion in mathematics called topological spaces. Then I want to explain a little where this notion of condensed sets comes from. So what's the origin of this, which is exactly coming from these p-adic numbers. And at the end, I want to maybe give a little bit of an idea of where one might use these ideas in other parts of mathematics. All right, so let's start with the introduction. Let me start around mathematics around 1900. So around this time, mathematicians try to properly set foundations for mathematics, try to axiomatize what they're doing. And they really have proper definitions of all the mathematical objects they are using. And one extremely basic notion is just that notion of a real number, which, as it turns out, is actually not as easy to define as you might think it is, because it's a very basic notion you learn about in school, and it's very, very intuitive. But actually, to properly define what a real number is takes real effort. And as I said, I will later in the talk expand on this point. And extremely influential in this area was Cantor's work, in particular on the notion of set. And somehow all of mathematics was then founded on Cantor's set theory. But the notion of a set is basically just points, but they don't speak to each other. They are just points, one alone, without any geometric structure to them. So, but the real numbers, they have a very visible geometric structure. You can say when points are close together. And so there's somehow an intuitive idea that some of there are neighborhoods of points. And this was encapsulated in the extremely influential notion of a topological space. And I think this definition goes back to Hausdorff in around 1914. Actually, mentioning Hausdorff and being at this event combining mathematics and poetry, I should also mention that Hausdorff was not only one of the world-leading mathematicians of his time, but he was also a poet. So he wrote several theater plays, several poems, most of them under pseudonym. I think Paul Mongrey, is that right? I might say it wrong. But this notion of a topological space is at the very foundations of mathematics and is really used in all areas of mathematics. You learn it very early on in your studies, and it's really basically used everywhere. However, in many areas of mathematics, even in topology itself, which is some of the area studying topological spaces, people are not quite happy with the definition of a topological space. And so in topology, they have a notion of a convenient category of topological spaces because the actual one is not so convenient. So there are certain persistent technical problems with this notion of a topological space. But people had kind of come to believe that this is just an inherent property of this mathematical idea of a topological space. Around 100 years later, there was a lot of work done in this geometry with these p-adic numbers that I will also explain a little later in my talk. And studying this p-adic geometry, this is related to these perfectoid spaces that Ulrike mentioned earlier, gave rise to the birth of a new concept that was a few years later given the term of condensed sets in my work with Dustin Clausen. This turns out to be extremely similar, to be a notion that's extremely similar to topological spaces, but with a kind of very different definition, very different perspective. So virtually everywhere you use topological spaces, you might as well use condensed sets, and basically they're more or less equivalent, so it doesn't really matter, but then they're yet slightly different. And the slight difference means that very often all the technical problems that you had, they just magically disappear, which was very surprising to me, and I think to many mathematicians, that you could just, by slightly tweaking the definition, make many of these technical problems magically disappear. And yeah, so this gave rise to this general idea of condensed mathematics, that you could try to apply this notion of condensed sets to various different areas of mathematics. And I want to talk a little bit about this today. But always, because it's somehow a different definition, it somehow always introduces a shift of perspective. You're always looking at things from a slightly different angle, and what seemed natural from the perspective of topological spaces may seem not so natural from condensed sets, and vice versa. Certain things that seem not so natural from topological spaces might seem natural from the condensed perspective. So you get a new perspective on very basic objects in mathematics. And so one of the basic objects you get a new perspective on, I think, are the real numbers. And basically the goal of my talk today is to explain the condensed perspective on the real numbers. All right, so this brings me to the second part of my talk about trying to recall a little bit of, this will all be extremely elementary school level material, some recollections about the real numbers. So let's recall a little bit about what numbers are and how to think of them geometrically. So maybe the first kind of numbers one learns about are the natural numbers, 1, 2, 3, 4, 5, and so on. And you may or may not consider 0 as a natural number, so it's kind of slightly blurred there. I mean, certainly in the history of mathematics, it took quite a while until 0 was considered to be on equal grounds with the others. And there's a way to think about this geometrically, which in particular is how the Greeks did it, like Euclid. So there, you fix some reference stick, say 1 meter or something like this. And then once you have this reference stick, you can start measuring things. And then try to measure how many meters this is. And this is probably slightly over 2 meters, but then you couldn't quite measure with a meter what the rest of this is. So if you just have one reference stick, then you can try to measure along a line. You can measure some integral distances from the origin. Of course, you could also go to the left, leading to some of the integers. Well, okay, that's by infinite. And some of the next class of numbers one learns about in school are the rational numbers, like 3/2, 9/7, and so on. How to think of those geometrically? Well, I could just make dots there where they are, but maybe this is not quite how the Greeks thought about this. So let me explain how actually in Euclid you think about the rational numbers. Euclid starts with something that actually comes back to this idea of reference stick. So somebody say, I have a meter, but then I go to England and they measure everything in foot. So then we have suddenly 2 reference sticks and we need to translate between our measurements. So it's a very practical problem to translate measurements between people using different reference sticks. And so to do that, would someone like to know how to do the translation? And the idea that Euclid uses, that nowadays might be called Euclid's algorithm, is the following. So assume you have 2 sticks. Then, if I now have also a shorter stick, I can first measure with my 1 meter stick that this is maybe slightly more than a meter, and then I can try to use my other stick and then try to measure this. But I can also use one of my sticks to try to measure the other. And so if I have my green stick here, well, it's slightly more than 2 red sticks, but then if I have both of these as measurement devices, then I can also measure this black thing here, which is the remainder. So I can somehow write the green stick as 2 times the red stick, and then I can make a new black stick, which is precisely the remainder that you have there. And then I have 2 smaller sticks. So now I have the red stick and the black stick. And I can try to do the same and try to measure the red stick in terms of the black stick. And if I'm fortunate, then at some point this will precisely close up. So in this case, I try to draw something where this basically ends up working. And so where the red stick is precisely twice times the black stick. And so then I can use the black stick as a common reference measure using which I can translate both other measurements in terms of the black one, namely the red one is just twice the black one, and the green one is 5. If you then replace these red ones by twice the black ones, this one totally 5 times the black one. So out of the 2, green and red, you can build a new one, a smaller one, which is the black one, and then the others are just multiples of this common reference one. And this is basically how the Greeks thought about the rational numbers 2/5. I mean, the red stick is about 2/5 of the green stick, meaning that you can find a smaller stick of which one is twice, the red one is twice it, and the green one is 5 times it. But they also knew that you won't always be lucky. This does not always work. And of course, the example here comes from the Pythagorean theorem. So if you have an equilateral triangle with side lengths A, B, and C, then the famous theorem of Pythagoras says that A squared plus B squared is equal to C squared. And fortunately enough, it turns out that you can find integers satisfying this, for example, 3, 4, and 5, which is very practical because it gives you a way to construct precise rectangles, because you can just do 3 times your stick, 4 times your stick, and then 5 times your stick, and then arrange that, and then you have a precise rectangle, which is, I think, how they even constructed precise rectangles back in the day. But if you do the same thing for a much more naive rectangle, which has both side lengths 1, then the other side will have a new side length, which we nowadays call the square root of 2. And now you can try to run this algorithm I talked about before. So you're trying to measure the red stick in terms of the green stick, and then, well, the green stick fits 1 times in, and then there's a remainder which somehow has length square root of 2 minus 1. And then you take your green stick, and then, well, this black stick turns out to fit twice in. And then there is a remainder that maybe you can't see, but it should be in blue. And then there's, now you have the black and the blue stick, and you can try to measure the black in terms of the blue, but again, there is a remainder. And you could keep repeating, and you would realize that at every step, somehow 2 times the previous one fits in, but then there is a little remainder, and this kind of repeats itself. So it turns out that the ratio between this green and the blue one is exactly the same ratio as the black and this remainder here. And if I would extend the previous one also to the left and by adding another green stick, then it turns out that this composite thing would also be precisely have the same ratio to this as to this. So the ratio of green plus red to black is the same as the green to the blue, is the same as the black to what remains here. And so this pattern repeats itself indefinitely. And so this algorithm will just never stop. If you think about what this means, it actually gives you some kind of iterative formula for what the square root of 2 is. Namely, if you're trying to construct 2 sticks which have ratio square root of 2, then you could say, well, okay, maybe this is really small. Let's just forget about it and let's pretend this was exactly twice times this. And then you could somehow have this stick, this twice, and so on. And iteratively construct the thing which leads to this continued fraction expansion, actually, that it's 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, giving you a very precise infinite formula for what the square root of 2 is. And you can just cut off this at some point, or here, or here. So for example, if I cut it off immediately, I would just get 1. If I cut it off here, I would get 3/2. If I cut it off here, I get 7 over 5. And you see that you get closer and closer, and actually really rapidly you get closer to square root of 2. So this is 1, which is a pretty bad approximation. This is 1.5, this is 1.4. I don't know exactly what this is, but you get very, very close to the square root of 2 very quickly. Okay, so the square root of 2 is not a rational number. This is, I think, how the Greeks proved that. So nowadays one usually explains a different proof of this, but I think this very geometric argument is how the Greeks thought about it. All right, so back to my table comparing numbers and geometry. So we have these rational numbers now. We have some way of thinking about them. So we can fill them into this line. But then we see somehow that not all the points are covered precisely because there are these other numbers like the square root of 2 that somehow sits somewhere also on this line but is not a rational number. And so we realize that if we really have this geometric picture in mind, that there is this full number line, then there must be more there. And the whole thing is what we think of as real numbers. And this is supposed to be the definition, but obviously it's not a mathematical definition because the definition appeals to our geometric picture of this number line. And it turns out that it's actually not so easy to make this into a precise mathematical definition. What you learn in school usually is that a real number is given by its decimal expansion. So in particular, like, there is a way to write the square root of 2 in terms of some like infinite decimal expansion. I think the first few terms are what I wrote, I hope. But then it goes on and on and on. I mean, it's not nearly as nice as the previous formula I find. This is 1 plus 1 over 2 plus 1 over 2, where you see an infinite pattern emerging. The digits here are just some random digits without any pattern to them, as far as anybody knows, and everybody's sure that there won't be a pattern there. Now, what does this kind of mean geometrically, this infinite decimal expansion? Well, the first one here precisely means that you're somewhat larger than 1 but smaller than 2, so you're somewhere on this interval. Okay, so let's zoom in on this interval. Let's make it larger. So zoom in. This is now the interval from 1 to 2, and now we can again space it into 10 pieces. So I'm picking a reference stick that's precisely 1/10 of the length of my original reference stick. And then the next digit 4 so means that I'm precisely on this interval here. Okay, so then I can zoom in again, and then I have this interval from 1.4 to 1.5 here. Then the next one means that I'm somewhere here in this interval, and so on and so forth. So you're somehow zooming in and zooming in and zooming in, and determining more and more precisely where your number is. But actually, so you might think that this way we uniquely prescribe any point of the real number line because we are precisely at each step prescribing on which of these intervals we are. But actually that's not what we're doing if we look carefully. Using the first digit in our decimal expansion, we're saying on which of these intervals we lie. Right? So if the first digit is 0, we're here. If the first digit is 1, we're here, and so on and so forth. And then the next digit somehow decomposes it further. But when we are precisely at 4, say, well, I mean, there are actually 2 intervals we might be on. We might be on this interval, or we might be on this interval. And we need to make a choice there, which interval we actually mean. So if you are given a decimal expansion, you cannot only produce a point of this space, which is what we wanted, but given a decimal expansion, you can also determine a point of this disjoint union here. Or really, in this space where you divided it even further, or even further. So a decimal expansion really determines a point not just of the real number line, but of an infinitely dissected real number line, where you cut your whole line into these unit intervals, and then each unit interval into tens of unit intervals, and each tens of unit interval further and further. So what decimal expansions really describe is not the real number line, but a certain infinite dissection of it. And to get back the real number line, we need to glue everything back together. We had these 2 intervals here, where we kind of cut the real number line at 4 to get this part and this part. And to get the real number line back, we need to glue this point to this point. And what does this mean in terms of the formulas? Well, what is this point here in terms of decimal expansions? Well, it's on this interval, which means it starts with a 4. But then afterwards, I always need to stay on the leftmost part. So I always need to put 0, 0, 0, 0, telling me after this, I'm always staying on the leftmost part. And what is this point here? Well, this is on the interval that starts with a 3. So it's the thing that starts with a 3 here. But then I always want to stay at the rightmost point. So then I always need to pick the last interval, meaning always a 9, 9, 9, 9, 9. But in the real number line, these were really the same thing. So I need to set them equal in the real numbers. And I think this is a point that's really confusing when you're trying to define real numbers in terms of decimal expansion, because you don't see why these two numbers should be equal. And then usually there are algebraic manipulations given that are supposed to explain why this is the case. But I think there's just a really geometric argument that they must be the same. Is that decimal expansions don't themselves describe the real numbers, they describe this infinitely dissected thing, and you need to glue this back together, which are precisely these weird identifications. And so the perspective you're getting this way on the real numbers is that the number line of the real numbers, which we really think of as a continuum, arises in a very weird way out of a completely infinitely dissected, totally disconnected space, where we dissected this infinitely often. And these things are described by decimal expansions. But then we need to glue things back together, which are precisely these identifications here. And this is what only gives us the continuum. Okay? So this was my digression on real numbers. And this somehow gives the lead to this discussion of the difference between this notion of topological spaces and condensed sets. And my discussion will not be technical at all. It will be at an extremely informal level. So I apologize to all mathematicians in the room. So what is this notion of a topological space? As I said earlier, it formalizes the idea that you have a set and you have a certain notion of neighborhoods. So here I was drawing the real number line. You have any point x on the real number line, and then you always have these small neighborhoods of this point. And these small neighborhoods are still nice spaces. Yeah? If you have a more complicated space like this cake, then the way you would somehow try to analyze this is you really look at the finished product and pick out small neighborhoods of a point by like taking a spoon and like looking at what you're getting and then analyzing these small neighborhoods. So some of the topological perspective on a mathematical object is that there is this finished product and you're trying to analyze it by looking at how it looks like near any given point. Okay? Let me contrast that with this notion of a condensed set, for which again I will only give an extremely informal discussion. So the way to think about a condensed set is that it's a baking recipe for how to build your desired object out of totally disconnected pieces. And we've precisely seen such a way in the case of the real numbers, where we had the totally disconnected piece, which were algebraically given by these decimal expansions, and which formed intuitively some kind of point cloud, or mathematicians call such a thing a Cantor set. Which is a bit unfortunate, because earlier I said that Cantor just defined abstract sets, but now there's also a specific thing called the Cantor set, which has some kind of topology on it. Sorry. But yeah, you have this totally disconnected thing, and then by doing these identifications I told you about, of identifying the endpoints of these intervals and also of these internal intervals, you're gluing this all together somehow. And then in the end you're baking the continuum out of totally disconnected pieces in a way which is maybe not so unsimilar to how you bake a cake out of like flour and sugar and other very disconnected pieces, and then you put them in the oven and then it becomes a nice continuum. Okay. So what's the advantage of this condensed perspective? The main advantage, maybe for me, I'm an algebraist, the numbers here is that hard, is that these totally disconnected pieces, they are extremely simple to describe algebraically. So one way that mathematicians used to do this is in terms of something called stone duality, describing them in terms of Boolean algebras. But really it's just what we've seen before. If we try to use algebra to describe stuff, something like decimal expansions, this algebra will always describe a totally disconnected space. You will not be able to directly with the algebra describe a continuum. So some of these totally disconnected spaces, these are the ones which have a simple algebraic description. And this is at the heart of why these condensed sets turn out to interact extremely well with all sorts of algebra. And this is also where they've maybe found the most applications so far in doing some kind of very nice algebra with condensed sets, condensed Abelian groups, and so on and so forth. But from a geometer's perspective, it's extremely unnatural to think of the real numbers as a quotient of a totally disconnected space, because all the nice geometry of the real numbers, all this nice continuum structure is completely obliterated if you just infinitely dissect your space on and on and on. So from a geometric or maybe also analytic perspective, it's not so clear that this condensed perspective is good at all. And maybe I want to come back to this question towards the end of my talk. But this is my, from very, very far away, how you should think of a condensed set. It's some kind of recipe for building nice spaces out of pieces that are somehow geometrically not so nice, they are totally disconnected, but have a nice algebraic description. Let me tell you how this weird idea originated. This comes from p-adic geometry. So the p here stands for a prime number that could be any one you like. My favorite is 2. But you could also take 3, 5, or 7, or whatever. Actually, anecdote, was once giving a course on algebraic geometry, and at one point I had to draw a space called spec Z, where the points are the prime numbers. And I was drawing 2, 3, 5, 7, 9. So I'm not so good with numbers. Also now I'm doing 10-adic numbers, and you will also realize that maybe 10 is also not a prime. It turns out that the basic structure of p-adic numbers works for any natural number n. You could have n-adic numbers. There is a certain reason that usually restrict to prime numbers, because then it's a field, otherwise it's not a field. So you can have 2 numbers which are not 0 and they multiply to 0, and maybe you don't want that. But if I would have to introduce p-adic numbers, I should first switch from the familiar decimal expansions of numbers to p-adic expansions for some other prime p, and this is just a further layer of technical complexity that's somewhat irrelevant to the story, so let me not do it. And instead talk about 10-adic numbers directly. And so one way to think about them is that they're really just like decimal expansions of real numbers, but instead of going infinitely far to the right, you go infinitely far to the left. Now, this doesn't seem to have any geometric meaning whatsoever. It's hard to think about what such a number should signify at first. But you can easily convince yourself that you can. It's very easy to do algebra with them, right? I mean, if I have such a number and I want to add this number to it, then I can just, 3 is 1, then 7 plus 4 is 1, and then I carry a 1, and then 1 plus 1 is 4, and then I don't know, and you can figure it out. It's even easier than the real numbers, because in the real numbers, if I start from the left and go to the right, I don't know whether I would have had a carry from the right coming up. So somehow if I want to get a specific digit in the real numbers, I would sometimes need to go infinitely far to the right to figure out whether there was a carry coming up forward to me. In the p-adic numbers, you don't have to do that. You can just start from the right, and you always know whether there's a carry or not. You can also do some funny computations, like if you take the infinite string of 9s and just add 1 to it, then 9 plus 1 is 10, so it's a 0, and then but I carry 1, and then 9 plus 1 is 10, so it's 0, and I carry 1. 99999 is equal to -1 in the 10-adic numbers, which seems a bit surprising, but it's true. So basically, if you, I don't know. It's very familiar that if you have like 1 and then lots of zeros, and you subtract 1, then you get lots of 9s, but then eventually something drops. But here, you can always borrow more. Yeah. So these weird numbers, they originated in number theory. And what they're really meaning is the following. If you're somehow only remembering the last digit of an integer, then you're only remembering the remainder when you divide by 10. So everything that ends with, like if you have 307 72 things, and you want to distribute them among 10 people, then you can do it evenly, except the 320 you can do evenly, but the last 7, they will be the remainder. So if you're only interested in, not in the precise natural numbers, but only in their remainder modulo 10 or modulo 100 or modulo 1000, then this is precisely kept track of in these p-adic numbers, or in these 10-adic numbers in this case. So they can be thought of as a way of keeping track of these remainders modulo division under all powers of 10. Note that precisely because you can always, like this issue with carrying doesn't come up, you actually do not need to make any of these weird identifications like 0.999999 is 1.0000. So the 10-adic numbers, they are literally what's the digital expansions. They are the same thing. You don't need to do any extra identifications. So the 10-adic numbers, they do form something totally disconnected. So if I try to draw all the like 10-adic integers, then here are all the ones that end with a 0, here are all the ones that end with a 1, here are all the ones that end with a 2, and so on. And I don't need to do any identifications here, because really they either end with a 0 or end with a 1 and no identifications. And if I was drawing the 3-adic numbers instead, then one way to visualize this is very much in terms of these circle, and then there were 3 circles inside, and then each of these 3 circles, you had 3 circles again in Oswald Egger's talk. So this picture of these circles inside circles is one way to visualize what the 3-adic numbers would look like. And you see that if you work with these p-adic numbers, then it's actually a very natural idea to try to base everything on these totally disconnected sets, because after all, that's kind of what your geometry is. So condensed sets somehow turn out to be very convenient in p-adic geometry and in p-adic analysis. I think I will end too early, but you didn't stop me, so the outlook. I was saying that some of the condensed sets, they are extremely natural from the perspective of the p-adic numbers, p-adic geometry. But from the perspective of the real numbers, they somehow feel less natural precisely because it doesn't feel so natural to take the real numbers and infinitely dissect them. And in particular, it was not so clear whether the condensed perspective could be fruitfully applied, in particular to analysis over the real numbers. So analysis over the real numbers is very much built on these notions of Banach spaces, Fréchet spaces, and so on. So there's all this functional analysis of these big topological vector spaces. There's a huge edifice of structures there. But this all feels a little bit unnatural from the condensed point of view. So from the condensed point of view, you would like to do this slightly differently. And then Dustin Clausen and we had some kind of idea of what the natural expectation would be for how you should do things. And we tried to prove this. And then we realized it's wrong. I will explain the basic reason it is wrong on the next slide. So it turns out that usually the basic desideratum one has about topological vector spaces of the real numbers is a condition called locally convex. Whatever this means. So basically, if 2 things are small, then if you draw a straight line between 2 small things, everything on the line should still be small. Or if you just have any set of small things, then if you form the convex hull of all these small things, everything in the convex hull should still be small. But it turns out that if you restrict to this locally convex setting in the condensed world, this is not a good condition. It violates certain things you would really like to have. And so this was quite a, I don't know, I was very frustrated when I realized that this does not work. And then we kind of tried to like make a deal with the devil and like just said, well, maybe not locally convex, but just a tiny bit less than that, and then maybe it still works. And then like the obstruction that we had wasn't there anymore, but we still couldn't prove it. And we tried, I spent basically a full year obsessed with trying to make this work. So we tried really hard to find a proof of the slightly weakened statement without ever being sure that it should be true, because the original hope was wrong, and then we're just, well, if x is wrong, then maybe x minus epsilon is still true. Let's hope for the best, but without any good reason to hope so. And trying to prove it, we were led into all sorts of really strange considerations where we tried to prove the thing about the real numbers by trying to prove a thing of arithmetic origin instead, where we had some kind of power series with integer coefficients instead. It all felt really, really strange, and at the end, we found an argument, but it was extremely complicated because it involved really, really difficult algebra combined with really difficult analysis and just barely chained together. It was a really, really fragile argument. But we could prove that if our original hope was wrong, then the original hope minus epsilon is still true. And this is the theorem I mean up there. But I was so unsure about my own argument that I somehow asked for a formal verification of this proof. And this was this liquid tensor experiment that Ulrike mentioned. And so in a very reasonable time frame, several mathematicians, led by Johan Kommelin in particular, were able to fully formalize the key statement. In particular, this thing where there's this very, very fragile combination of difficult analysis and difficult algebra in a formal proof assistant. So now I'm reasonably confident that this is actually true. But as I said, taking this condensed perspective on like real functional analysis, your changes how you look at things. And in particular, one new thing that's really convenient for doing algebra is that you can always form so-called quotient spaces. So quotient spaces are spaces where you somehow identify any 2 points in here whose difference lies in the image of this guy. This is a little bit like remainders modulo 10. You embed the integers via multiplication by 10 into itself, and then the quotient are integers mod 10. So it's a nice quotient space. So two spaces that are like the nicest kinds of topological vector space you might maybe think about are these LP spaces of sequences. So here you just have sequences of real numbers which are summable. So the norm of the absolute values stays. If you sum them all up, it's still finite. So in particular, you can form the sum of all the xi's and still get a real number. On the other hand, you could ask a slightly weaker condition, just that the sum of the squares stays finite. It turns out that whenever the sum is finite, the sum of the squares is finite too, but not conversely. And an example of this is the sequence 1, a half, a third, a fourth, where one learns that if you're trying to sum them all up, you get what's called the harmonic series, and this diverges to infinity. But if you take their squares, then it does turn out that it converges. This is actually related to the zeta function that also was mentioned in the last talk. By Euler, you get pi squared over 6. If you sum all the squares, you get something finite. So this is a strictly larger space, but this has Dan's image. So whenever you have any sequence in here, then you might then the point that's very, very close is if you keep the first 100 terms and then set everything else to 0. That certainly is summable, because you just have finitely made terms, so it's summable. And any point in here can be arbitrarily well approximated by all points in here. And so if you think topologically, then if you try to form the quotient space of L2 by L1, then this has no interesting topological structure, because if you take any point in the space and then look at any possible neighborhoods, then the neighborhood will be everything. Because, any 2 points are somehow arbitrarily well approximated by something in here. So if you subtract that, then you can make the difference arbitrarily small. So as a topological vector space, this just has no interesting structure at all. But it turns out that in condensed vector spaces, this just has a perfectly well-defined condensed structure. Basically, I told you the baking recipe. I told you what L2 of n is, I told you what L1 of n is, and then the recipe to bake it is just to take the quotient. It is a well-defined recipe, and you can work with it. But if you have such weird quotients, then you suddenly also get, you have new objects, but you also suddenly get new surprising maps. For example, there's the following funny map. You can take, again, these L1 sequences, so these summable sequences of real numbers. And now I'm defining a map to this weird quotient space. Okay? And what I'm doing in every coordinate, I'm doing something that I shouldn't be allowed to do when I do vector spaces. So vector spaces are supposed to have some additions. All the maps are supposed to be linear. But now I'm doing this very weird thing of multiplying x by the logarithm of the absolute value of x. So this is very much a nonlinear map. Okay, but you can still write it down. And this is always, turns out, this always defines a sequence in here, but I'm somehow only considering it up to summable sequences. And if I wouldn't do this up to summable sequences, then this absolutely would not be an additive map, just because somehow x times log x is not additive. But it turns out that up to summable sequences, it is an additive map. So if I take two sequences, and either I first apply this funny x log x map, or I first sum them and then apply this map, then the difference between these is, it turns out, always summable. So it is a additive map. It's linear under multiplication by real numbers. It is a map of condensed vector spaces. So this is a map in this new category that's somehow continuous and additive. So it's somehow a map that I don't think you could see in any formalism before. This kind of map, x times log x, is actually very much related to the entropy function defined by Shannon, which is exactly the sum of the xi log xi. So it has some kind of mathematical meaning, I think. And now this is a phenomenon that only exists in the condensed world, but we can use it to recover phenomena known in the classical world of topological spaces. And now here I'm really using a little bit of more fancy algebra. So maybe this is not for everyone now, but so you have this map from L1 to this quotient space, which was precisely the quotient of L2 by L1, which is what this kind of sequence here signifies. And you can take the pullback short exact sequence, where you take this thing projecting onto here. So this E will be elements in here and elements in here, which map to the same element in Q. And then it turns out that this will always produce now an extension of this guy by the same subspace here. So you get an extension of a Banach space L1 by another Banach space L1. And now, what's so weird about this map, that somehow there are these non-additive maps inside of here, means that this guy here is now a little bit of a strange topological space. Namely, this is not anymore a locally convex topological space. It's not a Banach space anymore. So we somehow started with the nicest kinds of topological spaces one has, Banach spaces, and just played around a little bit with them. And then in condensed world, we suddenly could cook up a new kind of topological vector space which falls out of the category of Banach spaces. And the existence of this E is what meant that our original hope was wrong. So this E basically goes back to the work of Ribbe from 1980. So it was known in functional analysis that you can have these things. And this meant that our original hope wasn't quite true. But somehow this is not too far from being locally convex. And so then we kind of hoped that if we slightly weaken our condition, it still works, and it did work, but the argument is really, really difficult because real functional analysis just becomes much, much harder outside of the locally convex setting. Many of the basic tools you use in real functional analysis just completely break down outside of the locally convex setting. But the possibility now that we can successfully apply the condensed formalism to real functional analysis turns out to be exactly what was needed in order to import a lot of tools that exist in this kind of more algebraic kind of mathematics, in particular in algebraic geometry, and move them over to the geometry and analysis over the real numbers. And one thing in particular you can do is you can combine tools that have been now successfully developed for applications of algebraic geometry, in particular also higher category theory. But you can now marry this with techniques from functional analysis. And usually these two, like this is something extremely algebraic, this is something really analytic, and the algebraic and analytic world usually don't mix so well. But in this framework they do. And it's just one possible outlook where such a thing might be useful. And I think physicists sometimes for quantum field theory need something like this, because there are some people studying quantum field theory really from a very analytic perspective. I mean, there's really non-trivial analysis going on there. On the other hand, algebraic topologists realize that quantum field theories are also extremely closely related to higher categories. But it's really hard to mix these two aspects of quantum field theories, I believe. But in the condensed formalism, it is actually quite easy. And so condensed mathematics might have applications in condensed matter. All right. So that's the end.